Welcome back, grade 12 learners and grade 11 learners and teachers alike. We are again going to contemplate on acids and bases. This is one of the section in paper 2 chemistry, which is relatively very easy because if you are doing grade 12, it is a repeat. Almost 80% of it, 20% will be just a work of grade 12. But now let's accommodate the two grades. So starting afresh, we say, when we talk about the pre-knowledge of this one, we'll go back to grade 10 and say, somewhere in grade 10 we were told of reactions of acids. Very important part in grade 10 now about this. Besides, many people say no, acids are in sour taste, and then the bases are bitter. Many of us, we don't know the difference between sour and bitter, but anyway, most important will be the reaction of acids. So besides acid turning litmus red and bases turning litmus blue, the litmus in acid is red and in base is blue. So blue, fine. That's what we were testing acid and base in grade 10. But most important one was this reaction of saying when a metal react with an acid, it will form metal salt plus hydrogen. I mean that in the laboratory, if you want to form hydrogen, you have to react an acid with a metal. For example, we'll be having your magnesium solid plus your HCl, which is a liquid or aqua solution, and then it will form magnesium chloride, and then which is a solution, then plus hydrogen gas. You'll see the bubbles in this case. If I got this, you just put a rod of magnesium in the HCl, then you'll see those bubbles around the rod. That is the formation of hydrogen gas. Fine. Number 2 is when the metal oxide, it's rarely used this one, plus acid, it forms metal salt plus water. So if you have magnesium oxide, which is a solid, and then reacted with HCl, which is a liquid, and then it form magnesium chloride solution plus water, which is a form of it, which is a liquid. Fine. The most important reaction in this section is then this one that follows, to say when an acid react with a base, it forms your metal salt, yes, plus water. Why this is important? Because this is what we are dealing with in this section. We are reacting acids and bases, and this is called neutralization. The neutralization reaction, they can ask you the name of it. An example will be when your HCl, which is a solution liquid, and sodium hydroxide, which is your solid, if they react, will form sodium chloride solution plus water, the form of a liquid. Fine. That is the most important one. So in this case, remember, the base is neutralizing the harmfulness of the acid. So that's called neutralization or ion exchange in the lower grades. And then the last one is when an acid react with a carbonate. It will form metal salt, and then plus water plus carbon dioxide. Very important. This is the reaction that you can even test whether your stomach acid is in excess. You can always take a carbonate with relatively milk, And then in this case, we'll say when I've got HCl reacting with the calcium carbonate, it will form calcium chloride plus water plus carbon dioxide. That is the most important one. To say we call it gas forming. If they can ask you about the reaction, normally it's a gas forming. So we are forming a gas, same as the first one. They are gas forming. This one, where now we are producing hydrogen. I think very important reactions of acids. Now, when we get to grade 11, we introduce to acid-base models. Acid-base models or theory is fine, theories. Now, what are the acid-base models? We have got the classical one, the old one, which is your Arrhenius theory or model. What says Arrhenius? According to Arrhenius, an acid is any substance that forms or produces hydronium ions in water or in solution. And whereas a base will be any substance that produces OH minus hydroxide ion in water. Then we say that substance is an acid. Like in this case, if I've got maybe HCl plus water forming hydronium ion plus Cl minus. In this case, I can have sodium hydroxide. When it reacts with water, it will form your sodium ion plus OH minus. So any substance that produces OH minus is a base. Upon this one, that's where now in this then came the modern theory, which reviewed this stance to say no, not always that the base will produce OH minus. The so-called Lorry-Bronsted, this one repealed the second definition, Lorry-Bronsted theory. They came up with a new version to say all acids donate protons. All acids donate protons, therefore they are called proton donor. And then whereas in this case means that if I've got HCl plus water, then it will form hydronium ion plus Cl minus. So the H plus will move from here to here. Therefore the H plus is a proton. Therefore the acid donated proton to water so that water can form this. And a base, according to Lorry-Bronsted, a base will be any substance that receives protons. They are called proton acceptor. That's two words, very important to say. Like in this case, you can see that water receives the hydrogen, therefore water becomes a base, and then HCl is an acid. I think with the acid base we are done. What next now? After knowing this one, we can now identify, separate between this one, strong acid and a weak acid. What is a strong acid? We say this one is the acid that ionizes completely in water. And now of late we need to now put the second phase and produce or form high concentration of hydronium ions. Therefore that is a strong acid. Whereas a weak one will be strong acid. Remember, example here will be having your HCl, your HBr will be having your sulfuric acid, will be having your nitric acid. Those are examples of strong acids. Whereas weak acids are the ones that ionize incompletely, completely, or partially. If your English is okay, you can use the word partially in water to produce and form low concentration of hydronium ions. Then in this case, for example, we will be having which acids are in a way weak. Remember, all organic acids are weak, including this one, which is ethanoic acid. Oxalic acid is weak. We have got also phosphoric acid is weak. We've got carbonic acid is weak. There are many. Sulfurous acid is weak. So those are typical weak acids. Weak acids in this case, no problem, and including your ammonium chloride as well. Those will be also your weak acids. Fine. Now, can we differentiate in closing now of the first part between concentrated acid and a weak acid? There was a statement here which says dilute sulfuric acid is weak. Now, do you agree with the learner who says dilute sulfuric acid is weak? Let's see. What is a concentrated acid? By definition, concentrated acid, we say it contains a large amount of acid in proportion to the volume of water. So which is your C equals to N over V. We are normally doing it from that perspective, whereas a dilute acid, therefore it will be the opposite. This one will say now it contains small amount of acid in proportion to the volume of water. Very important. Of water. Therefore, when we are diluting the acid, we are not tampering with the strength of the acid. Sulfuric acid naturally strong, whether dilute or concentrated is strong. So, but the concentrated sulfuric acid is just having a higher concentration, and the dilute is just having low concentration. Therefore, that is why we'll say, if we dilute the acid, you will find that if I've got a teaspoon of sulfuric acid, I add it to water and then form maybe 1 liter of dilute acid. Therefore, we'll agree that the number of mole of the concentrated is the same as the number of mole in the dilute solution. The same particles. So I've got 5 ml here, therefore 5 ml plus maybe 995 mLs. Then it makes this one. So I still have got 5 ml of sulfuric acid in this one. Hence, the formula of CCVC equals to CDVD. Because this one we are not used to it, we normally just write it as C1V1 equals to C2V2. Very important formula for dilution of an acid. So we'll be dealing with calculations in relation with this as time continues, to say how do we move. If a learner now has got in the lab, maybe you can just circle around this one. I've got hydrochloric acid, which is 10 mole per dm cube in the lab. I need this one to add it to water. I need to create a dilute solution of HCl, then with a concentration of 0.1 mole per dm cube, but in a 250 cubic centimeter of volume. The volumetric flask, which is your Erlenmeyer flask. Now they say calculate the volume of the concentrated acid and the volume of water required. So in order to deal with this one, you just go to the same formula to say C1V1 equals to C2V2. Therefore C1 we know is 10, V1 we don't know, C2 we know is 0.1 multiplied by you can just write 250 or write 0.25. So it will be giving you the same, because there's an argument of, say, since there are two volumes, cubic centimeter will cancel out, and another argument of, say, oh fine, to find the number of moles, then you need to multiply concentration by decimeter cube, not by cubic centimeter. So there are always those two schools of thoughts. So V1 will be the same as now. In this case, 250 multiplied by this one divided by 10 will be around 2.5 cubic centimeter, which is half a spoon. Then now the volume of water, remember in the 250 we have got volume of water, so the 250 cubic centimeter is the volume of water plus the volume of the acid, which is 2.5 cubic centimeter. Therefore the volume of water will be now 247.5 cubic centimeter. So that is how you deal with this type of calculations now. Hopefully when time continues, we'll also deal with questions that are integrated in an acid-based question in a formal question paper. But for now, I think we have done justice up to concentrated and dilute. So in continuing, then we'll talk about the aqueous solutions now. So as aqueous solutions of acids, of solutions of acids and bases, so which will lead us to conjugate acid-base pairs. So until next session, bye.